Okay, so if the output is a continuous value, in this case a scalar, it's the same idea. We want to, the correct answer is here, and the energy is actually higher than other values. We'd like to pull up on energy of things that are wrong and have low energies, and push down on the energy of the correct answer, so that eventually the energy function looks like this. Okay. Okay, so one thing that's important to remember here is two concepts, right? One is the energy function. When we minimize the energy function, we do inference. And the second one is the loss function, or objective function. And when we minimize it, we do learning. Okay. Okay, so we need 4 elements. First is an architecture, which is a particular form for E, and we'll see a few examples. We can put, this function can be very complicated. It can have a convolutional net in it or something like that. The second one is we pick an inference algorithm for Y, so it's whatever algorithm we use to find the Y that minimizes E for a given X, and the current value of W. It could be an approximate inference algorithm. And again, there's lots of different ones. That's called maximum a posteriori, which means minimization. B propagation, B variational methods, gradient descent, NTT. There's all kinds of stuff, right? The thing we need is to pick a loss function. So the loss function is going to, again, take as parameter the desired answer and the energy for as a function of that answer. And it's going to shape, when we minimize it, it's going to shape the energy function so that it gives us the right answer. And then we need an optimization algorithm to minimize this loss function with respect to the parameter of the energy. So now we have to ask ourselves, how do we design loss functions to do the right thing? So here's an example. This is for regression. Okay, it's a very simple example where we have an input variable x, we have a variable to be predicted y. Both of them are inputs, again, to the energy function. And here we have 2 energy functions. This guy and that guy, they both correspond to the same mapping of x to y. Okay, so if in fact, the mapping from x to y is y equals x squared. So if I take a particular value of x and I look for the value of y that minimizes the energy for that x, I find this boolean here, which corresponds to y equals x squared. Same for here, I get the same answer. Okay, so the inference algorithm, the minimization of the energy over y here gives me the same answer for those 2 energy functions. But notice that those 2 energy functions are very different. So this one actually is quadratic as a function of y for a given x. This one kind of saturates. This one, when I compute the Gibbs distribution, P of y given x, by taking exponential and normalizing for all y, I get a Gaussian distribution because the exponential minus of a quadratic function is a Gaussian. Right? So here, the P of y given x is a Gaussian. Okay, it's a Gaussian model. Here, I can't actually compute a probability that corresponds to this because the denominator is infinite. It's because the function here saturates. Right? So if I integrate this over the entire domain, I get infinity. And I can't really turn this into a probability distribution given the Gibbs formula. So this is an example of energy function that's outside the scope of probabilistic models, if you want. But it's still fine, it gives me the right answer. Yes?
Sorry, what do you mean when you say saturates?
Well, you see, it doesn't go above a particular value. It's kind of flat after a certain distance from the samples here, the training samples. It gets flat. Okay? And so when I take e to the minus this flat part is going to be, e to the minus some constant. If I integrate e to the minus, so that's a constant. If I integrate this over the entire, over R, I get infinity. Right? So I can't use the Gibbs distribution to turn this into a probability distribution. I can use tricks to do this, but I could limit the domain, for example. Yes?
Well, you said if you have a numerator in the if you have a constant in the numerator at that point, is the integral also going to be constant if it's over a bounded area?
Well, the thing is,
since the function is saturated.
okay, so notice that this energy function I showed is actually an asymptote, so it's not actually exactly flat. It just, you know, gets very close to be flat. It's actually the same as the one on the left, passed through a sigmoid function. So it saturates, but it's never flat. So the relative energy of different y's is the same. The ordering of E of y is the same as the quadratic function. But it's just that I can't compute this. This diverges now. Okay, so the reason for this example is to show that there are models that are not probabilistic models. I can't turn them into conditional probabilities, but they give me the right answer.
The
right?
domain is infinite.
If the domain is infinite, yeah. If the domain is finite, then you can always play games, right?
Okay.
Or you can add a regularizer to make the simple average. Okay, so how do we re-express some standard prediction models into this framework? It's very simple. So let's imagine we want to sort of re-express things we're familiar with, like regression and classification, in terms of energy-based models. It would go like this. So here is regression. So regression, classical regression, you take an x, you run it through some parameterized function. Okay, your regressor. And then you take the output of this, connect it to a distance measure, okay, which you should call a loss function actually. And this measures the distance between whatever comes out of this box and y, okay? And generally we make this function convex, say square. So this is least square regression. E of wyx is equal to 1/2 Euclidean norm square of the difference between y and GW of x. The GW of x is whatever comes out of this box. If GW of x is linear in w, then it's just linear regression with least square functions. Okay, so the inference algorithm here is trivial. If you ask the question, what's the value of y that minimizes the energy for a given value of x? Well, you just set the value of y to that, and then E of x is 0, and that's as low as it gets, right? So the inference algorithm here is the highly technical process that consists in taking whatever comes out here and copying it to y. Okay. Now, binary classification has kind of an interesting formulation where, again, you have a parameterized function. And again, these are examples. There are more complex ways of doing this, but you have a parameterized function, say linearly parameterized or not, or neural net, convolutional net, whatever it is. And y can take two values, +1 or -1. Or energy function is going to be -y times GW of x. So what this guy wants is that it wants y and GW of x to be the same sign. Y can only take a value +1 or -1, so if GW of x is positive, you want to set y to 1. If GW of x is negative, you want to set y to -1. Okay, that's the inference algorithm. So here, the inference algorithm is trivial. Again, run x through the GW of x function, look at this, take the sign of it, and copy this in y, and that's your inference algorithm. Rather trivial. For multi-class classification, you could think of this as kind of a binary switch. For multi-class classification, you need an n-way switch when you have n categories. So here in this case, 3. Okay, and this is a module that we've seen before. We've encountered this before in a previous lecture, the switch module. So y here can take discrete values for 1, 2, or 3, and GW of x puts 3 scores, which are energies for the 3 categories it knows about. And the inference algorithm here consists in finding out which of those 3 values is the smallest, and then setting the switch to that, and connecting the output to the smallest value. Okay, so this does the minimization of the y of E of wyx. Is that clear? Any questions? Any questions? Okay. So of course, those are trivial. You don't really need energy-based models to express those things. But I'll give you another example where it might be a little more useful. So here, x goes through a some sort of parameterized function, but y also goes through some sort of parameterized function. And there, what do we do? So the output of those two boxes goes into, say, something that measures the distance between those two vectors. Okay. In this case, the L1 norm, but it could be any distance. L2 norm would work too. So here, if I give you an x, it's kind of difficult to figure out which y is going to minimize this, right? Because this could be a very complicated function. In fact, there could be a whole bunch of y's that minimizes this, depending on the shape of that function. If this function is degenerate, if it's a many-to-one mapping, then it could be that there are many, many different values of y that give you the same value here that happens to be the same as the one on the left side. So I can't call this implicit regression. I'm not sure it's a good name, but so the advantage of this is that you could have multiple answers here that have low energy. That's kind of an advantage. It's not a bug, it's a feature. Okay, normally there would be an application here, an animation. Unfortunately, that's the non-animated version. Okay, so let's say, let's take a simple example here, two simple examples to see what problem we're facing when designing loss functions. Okay, so here we have the neural net. We plug it into a distance, say 1 or 2, whatever, square error. So in this case here, it's L1. It's the absolute value of the difference between the output we plug here and the output that comes out of this box. And we get this kind of energy function here. So these are the training samples. Okay, and this is the starting state of the energy function. So basically, this function is flat, and as we're going to train this machine, this kink here at the bottom is going to move for every value of x. Is going to move towards the blue beads, so that it's going to form a groove around the blue beads. Okay. In fact, let me check if I have an animated version of this. Nicer. Okay, that's nice. All right, so you see the learning process here. We start from the straight line, and as the learning proceeds, the groove here moves towards the data points. Okay? The only thing I did here is that I used as a loss function the average energy that my system gives to each y. Okay? So my loss function here, which I call the energy loss, is simply what energy does my system give to the correct answer. That's it. Okay, so it wants to push down on the energy of the correct answer. And so, and that's classical regression will do this. Okay, that's typically what the classical regression will do. So basically, it changes the parameters of this regressor here, neural net in this case, so that the blue beads are as low as possible. And it works fine because the shape of this energy function as a function of y for a given x is constant. It's just the only thing we can do is move the output of the network. The shape of the function as a function of y is constant. It's got a minimum at the output of the network, and then it goes up in a V shape when we go from side to side. Okay, here it's slightly more complicated and it doesn't work. So here I'm also minimizing the average energy of the beads, and a catastrophe happens, which is that the energy function becomes completely flat. And the reason here is that we call this a collapse sometimes. There is nothing that prevents the system from essentially ignoring both inputs, setting the outputs of those two neural nets or regressors to the same value, constant value. And now you get zero energy on average, but you get zero energy for everything. You get zero energy for the correct answer, you get zero energy for everything else as well. Okay? So what's missing here is another term. You don't want to just make the energy of the data points as low as possible. You want to make the energy of wrong answers also high. And this actually doesn't do this for you. It just pulls down the energy of the correct answer. Here it worked because the energy was designed in such a way that only one value can have low energy for a given x, and so the other ones necessarily have higher energies. But here, that's not the case. They could be zero. In fact, we observe this collapse. So, how do we fix this? Well, here is another example, and this is a very common example. It's the perceptron loss. Okay, so you've all heard of the perceptron and the perceptron learning algorithm, and certainly the perceptron loss function that the perceptron minimizes. This is a generalized version of the perceptron, if you want, the perceptron loss, written in a slightly different way than usual. So here what we say is that the energy that our system gives to the correct answer, which is E of yi xi, okay, so this is the data point, should be as small as possible. But then the energy of whatever y already has the lowest energy should be as large as possible. There's a minus sign here, so to make this difference as small as possible, we need to make this small and this large. Okay? So if you have a point that is not the correct answer and has lower energy than the correct answer, this difference is going to be positive. This guy has higher energy than that guy. This is the energy of the answer that the machine produces, right? Okay, because the inference algorithm minimizes over y, so here what we get is the energy of the answer the machine produces. And this is the energy of the correct answer. If the difference is positive, that means the answer the machine produces has lower energy than the answer we want. Okay, so again, we push down on the energy of the correct answer, push up on the energy of the incorrect answer. So minimizing this difference is going to push down on this energy, push up on that energy. Okay? Should work, right? Okay, it doesn't actually work that well. I mean, it works in certain situations, particularly, there is one particular case where it actually works, which is the case where the energy function is a linear parametrization is linearly parameterized in W. In this case, it works. But if E is some complicated function of W, maybe a neural net, plus some sort of energy function on top, it may not work. It may still have this collapse problem, because this does not push the energy of the correct answer to be strictly lower than the energy of everything else. It's zero if they are exactly the same. Okay, so you can still have a collapse here. So it works better in practice, particularly if the energy parameterization does not allow for flat surfaces, or if, which is the case when E is a linear parameterization, is linearly parameterized in W. So let's see how this translates into the real perceptron. Okay. So here is the loss function of the perceptron. We're going to define our energy like this. This is the binary classification energy that I mentioned earlier. Okay. So y again is a binary variable. Takes a value +1 or -1 depending on the category of x. So for inference, we're going to find the y star, which is the value of y that minimizes -y GW of x. And as I said before, that's simply the sign of GW of x, where sign is +1 when the argument is positive, -1 when the argument is negative. The perceptron loss then can be rewritten as follows. It's the sine of GW of x minus y times CW of x, xi. Okay, because we get y times GW of xi inside of this. So that gives us, and then here we have the sine of GW of xi, and here we just have yi. Sorry, here we have yi, and here we have the sine of GW of xi, so that gives us this difference. And then this term here gives us that term. Okay, so that's the error term, and that's the thing. So now if we define, so we have a learning rule, which is the generalized perceptron learning rule. That's not assuming anything about the form of GW, other than the fact that we could compute some sort of gradient. If G is linear in W, then we can write it as W transpose phi of x, where phi is a set of features that are previously being extracted from x. And now what we get is the linear perceptron learning rule. Any question? Okay, no question? Give a break. Okay, so here is another loss function that actually is considerably more useful because it doesn't fall victim to the collapse problem, but it's still relatively easy to understand. And it's called a generalized margin loss, or sometimes people call it structured SVM or whatever, but it's kind of more specific. It's really like a margin loss similar to what is used in supervector machines. And for this, we need to define, in the discrete case, what's called the most offending incorrect answer. So this is, among all the possible values of y in the discrete case, there is one that happens to be wrong, but has the lowest energy among all the wrong answers. Okay? So you ask the machine, is this a car? And it tells you it's an elephant. That's the most offending incorrect answer, because energy of elephant is the lowest energy among all. Okay? Or sometimes it tells you it's a car, but then the elephant is the second, the runner-up. Or runner-down, because it's energy. But, so that elephant would be the most offending incorrect answer. Okay? So the answer of lowest energy, that happens to be wrong. It's different from the correct answer. Or from one of the correct answers if there are multiple correct answers. In the continuous case, it could be a little more difficult to define. In fact, there is a better way of defining all of this, which I come to later. So here you might want to define a little sphere, ball around the correct answer, and say, anything that has the lowest energy outside of this sphere is my most offending incorrect answer. In fact, the proper way to do this is a little different, but let's stick with this for now. So the generalized margin loss is something like this that says it's a increasing function of the energy of the correct answer and a decreasing function of the energy of the most offending incorrect answer. Okay? And it's designed in such a way that the loss takes its minimum value when this guy is lower than that guy by at least a margin n. Okay, so let's do a little diagram here. So this is the energy of the correct answer. This is the energy of the most offending incorrect answer. What we like is that the loss function takes its minimum value in this region, above the dotted line here, where the distance between the dotted line and the continuous line is m. Okay, so here, to get the lowest loss, the energy of the correct answer has to be lower than the energy of the incorrect answer by at least m. Okay, so in fact m is just the distance between these two lines. And the only thing you need is that when you are on this side, the loss function increases. Okay, so that when you do gradient descent or whatever logging, the system is going to push you towards this region. Right? So here's a simple example. So this, if you apply this to the binary classifier, you get a supervector machine. If you have an L2 regularizer for the weights. It's the hinge loss. So the hinge loss is the positive part of the difference between the energy of the correct answer minus the energy of the most offending incorrect answer plus m, which is the margin. You can, again, if there is an arbitrary scale in E, you can set n to 1 arbitrarily and not worry about it. Okay, so that's the loss. That's the difference between the energy of the incorrect answer, most of the incorrect answer, and the correct answer. And it wants to make this difference negative. So this one has a well-known margin m. It's set by this cost. Okay, here is a second type of loss function we can use. This one is very similar to the logistic regression loss for two-class classification, where so we call this sort of log loss or soft hinge. And this is the log of 1 plus the exponential of the difference between the energy of the correct answer and the energy of the most offending incorrect answer. So instead of a sort of hard hinge, we get this kind of soft hinge that asymptotes a 0 on the negative side and asymptotes the identity domain diagonal on the positive side. And if you plug a linearly parameterized energy here, which is minus y w transpose 5x, what you get is two-class logistic regression. So here's another example of loss. This is it's called square loss. So it's a funny kind of margin loss here, which says I want the square of the energy of the correct answer to be as low as possible, and then I want to push up the energy of the incorrect answer, the most offending incorrect answer, with a kind of a quadratic term that kind of saturates above m. So essentially, you want the incorrect, you want the energy of the correct answer to be as close to 0, and you attract it to 0 with a quadratic term. Okay, so energies are always positive in this case, for example, because it's a square. So you have some energy, you have a quadratic cost as a function of the energy that tries to attract the energy of the correct answer towards 0. And then the second term says, I'm going to put a parabola with the minimum at m, but I only care about the negative part of the parabola, right? So the parabola goes like this, decreases, and then stops at 0, and that's the energy of the most offending incorrect answer, right? So the energy of the correct answer wants to go to 0, the energy of the most offending incorrect answer wants to go to m, both with quadratic cost, and the correct answer can go below 0, the incorrect answer can go above m if it wants to, it's flat. Okay, square loss. So here is an application of the square loss to this little example I was showing you earlier. And here, I defined the most offending incorrect answer as something kind of near one of the beads at some distance away from it. And so what it does is that it pushes down on the energy of the blue beads, and it pushes up on the energies of points that are some distance away from the blue beads. Okay, whatever value is smallest some distance away from the blue bead. And as it proceeds, the function takes a right shape. Okay, so this is the same example that I showed earlier, where you could have a collapse if you just minimize the average energy of the blue beads. But here I'm pushing up also on the energy of points that are outside. So it does the right thing. So the contrastive term here does that. It pushes up on the energy of things outside the data. Okay, so now, now I'm going to mention very quickly that this analysis here is not specific to supervised learning, but it works just the same for unsupervised learning. All the formulas I've given you so far are valid, and to turn them into what they should be for unsupervised learning, you get rid of x. Unsupervised learning is when you only have a y. Okay, it sounds counterintuitive. You say, well, unsupervised learning is when I only have an x, I don't actually have an output to produce. But actually, unsupervised learning is when the only variable you want to produce is something that you may observe. Unsupervised learning is discovering the structure of input data, of data, and so it's like predicting some subset of y from another subset of y. And so the only variable you want to predict is y. So let's imagine now that we don't have an x. We have two y's. Okay, you have two. Y is now a bidimensional variable. So this is y1 and y2, for example. Okay, and these are data points. And what we're trying to do is discover the structure of this manifold, this data manifold. Okay, so this is going back to stuff I was talking about a few weeks ago, where natural data lies in a low-dimensional manifold. So here is how we would perhaps discover, parameterize a low-dimensional manifold using an energy-based model. You have a bunch of data points, and you want to build a box that gives low energy to the data points and higher energies to everything else. Okay, and in the supervised case, we consider that one of the variables is always observed and the other one is one we predict. In the unsupervised case, both variables are things we want to predict. Okay, we could either predict one from the first one from the second one, or the second one from the first one. You could think of unsupervised learning as that, predicting a subset of variables from another subset of variables. But other than that, the formulation is identical. Okay. Here are other margin-like losses. And I list them here for the sake of completeness, but really, some of those are not particularly used. Some of those are used only in the context of speech recognition, for example. So LVQ2 is actually a very old type of loss function. It wasn't formulated in terms of those energies back then, but that's what it comes down to in the end. So LVQ means learning vector quantization, version 2. It comes from this guy, Tehuvo Kohonen, who did a lot of influential work in the 70s and 80s. He's kind of retired now. And Xavier Driancourt and Léon Boutou, still around. He's at Microsoft Research in New York. So here it's a little complicated. It's kind of a normalized energy difference. So you want to make the energy of the correct answer low, the energy of the most affinity correct answer high. You kind of normalize by some sort of normalization term, if you want, that depends on the energy of the most affinity correct answer. I'm not going to go into the details of this. This one is slightly more important. So this one says, this one plugs the difference in a sigmoid function. So it says, I want this to be lower than that, but I don't care how much lower it is as long as it is lower. And the sigma here is a sigmoid function. So it says, if this is much, much larger than this, you pay a nominal price, namely 1, okay, because the sigmoid function here is equal to 1 when the argument x goes to infinity. So when this difference is large, it's very large, which means that this guy is much larger than that one, and you really get the wrong answer. You just pay a price of 1 in your loss function. And if this guy is much lower than that guy, then you pay a price of 0. And then when the difference is small, you pay somewhere in between 1 and 0. Okay? So you could think of this as a soft approximation to how many errors the system is making. Right? Because for every sample here, you're going to pay a price of 1 or 0, close to 1 or 0, somewhere in between. And so this sort of approximates how many errors the system is making. The problem with this is that when the difference is large and close to, that this guy is close to 1, the gradient is very small, so it's very kind of hard for this to train. But people have been using this in speech recognition to pretty good effect. Generally, training with this loss function follows another phase of training with a better behaved loss function. This is kind of for fine-tuning. Yeah, that's another one where you have a square for the attractive term and kind of a negative exponential for the repelling term. Okay, but here is a more popular one if you want, although it's got some major problems. This is the one you would use if you want to be if you want to build a probabilistic model. Okay, so if you want to build a probabilistic model, so I'm going to go through the whole derivation. Some of this you've probably seen in other contexts, perhaps in David Zontak's courses if you take it. Okay, so here what we want to do is we're going to express the conditional probability of all the y's in our training set, given all the x's in our training set and the parameters, the parameter of a model. Okay, so this is the joint probability of all the outputs, the desired outputs, if you want, that our model gives to all the desired outputs, given that it observes all the inputs. And we're going to assume the samples are independent, so this is going to factorize as a product over samples from I equal 1 to p of the conditional probability of yi, the prediction, I mean the correct answer for the ith example, given the ith example and the parameter. And I want to maximize this. We want to maximize this, we want to maximize that. That's under the independence assumption. Instead of maximizing this, we're going to minimize the negative log of that. So we take negative log of this guy. So the negative log of a product turns into the sum of the negative logs. Okay? So that's our loss function. So it's a sum or an average over samples of minus log the conditional probability of that our model gives to the correct answer given the input. Okay? So this p here, I always have to say this because the p, the probability notation is always ambiguous. It's never clear whether this is the real probability or whether it's the probability that our model gives. So when there is a condition over w, that means it's the probability that your model gives to yi, okay? So these are actual values. So this is a number. This number is the probability that your model gives to yi, given that it observes xi and that its parameter value is w. Right? It's not the real probability of the research itself. All right, so we decided early on that we're going to parameterize this as kind of a Gibbs distribution that is a function of or energy function. That's a good way of transforming energies into probabilities. So we're going to substitute this inside of that, and we get negative log of a ratio, which is going to be the log of the difference. Okay. So then we get negative log of exponential minus beta blah blah, minus negative log of sum over y of e to the minus beta blah blah, right? The log and the exponential cancel. And we're left with, and the minus and this minus cancel, so we're left with beta times the energy of the correct answer. We get this. And then the other term here, which is the negative log of, minus log of this, we get a plus log of this guy. Okay, so this is our loss function. In fact, I'm going to divide it by beta. It doesn't make any difference. Beta is just a constant, so I don't change the property of the function by just removing a constant. And I get this. So we call this the negative log likelihood, or some people call it maximum mutual information, but it's the same thing. It's 1 over p, sum for I equals 1 over 2p of the energy of the correct answer, plus a term that combines the energy of all answers, correct or incorrect. Okay? And this guy here is a log sum exponential. We've seen that function before, right? We talked about this a couple of weeks ago. So this is a function that combines all of those energies. And what it does is that it's a decreasing function of all of those energies. So what this guy is going to do, if you want to minimize this value, this whole overall thing here, you're going to have to make all of those energies large as possible. Okay? Because if you make those energies large, the exponential minus is going to be small, and then the sum of them all is going to be small, and the log is going to be small, right? So minimizing this term is going to make those energies large. It's going to push them to infinity, essentially. Now, one of those terms is this guy. Right? So this guy is not going to get, it's going to get pushed, but it's not going to get pushed as much as it's being pulled towards 0, or towards small values. And we're going to see this in a moment. Now, remember that we studied slightly the properties of this way of combining values. So when beta goes to infinity, the only term in this sum that counts is the term that contains the e of smallest value. Okay? The other ones are going to be much, much smaller. The exponential minus for all the other ones is going to be much, much smaller. Okay? Because the beta times this is going to be much, much bigger because beta is very large. Okay, so as beta goes to infinity, the only term that matters here is the term that contains the energy, the minimum energy, the energy that is produced by the y that has the lowest energy. Okay? So in fact, this whole thing collapses. So then the sum reduces to one term, which is e to the minus beta mean over y of e of that. The log and the exponential cancel, the beta and the beta cancel, and you get minus mean over y of energy of y of Wyx. And what you get here is just a perceptron loss. Okay? So for beta goes to infinity, this reduces the perceptron loss, but for non-infinite beta, it's kind of a soft version of perceptron, if you want. And it's kind of the correct probabilistic way. If you want your system to produce energies whose exponentials are good estimates of probabilities, this is the loss function you should use. Okay? If you don't care about probabilities, then you can use whatever loss function you want that, does it for you. So, okay, so it's worth studying this loss function a little bit. In particular, it's worth figuring out what's going to happen when we compute the gradient of this loss function with respect to the parameters in the system. And again, it doesn't matter what you have in this machine. It could be a complicated neural net or whatever. When you see this loss function, so for those of you who know what this is the loss function used by conditional random fields. This is also the loss function used by multinomial logistic regression. So in multinomial logistic regression, this would be the dot product between the weight vector and the feature vector for the correct category. And this would be the sum, the log of the sum for all categories of e to the minus the dot product of the weight vector by the feature vector for all the categories, including the correct one. Okay? And you can convince yourself that, by differentiating this and figuring out the gradient, you get basically multinomial logistic regression. It's not surprising because it's as if we'd stuck a softmax unit on top of our linear classifier, right? You think of this as a linear classifier, you put the softmax unit on top, and then you do, maximize the log of the probability of the correct answer, or minimize the negative log of it, and that's exactly what we get. Whenever this function is complicated and has structure in it, this is called, and whenever it's linearly parameterized in W, this is called a conditional random field. How many of you here has heard of conditional random field? CRF? Okay, like half the room. Okay, so CRF is a form of this where this function is linearly parameterized in W, but perhaps has some structure in it, so you need to minimize with respect to Y. Perhaps inside it has latent variables also, which I'm kind of hiding. And you use this loss function and that's CRF. Okay, so let's compute the gradient of this with respect to W, right? So differentiate this with respect to W, we get the, so it should be, so this is for the per sample loss. This is the average loss. The per sample loss is whatever is inside the sum, inside the parentheses here, so it's this capital L. So this term, you're going to get just the gradient of energy with respect to W at the training sample, xi, yi, okay? Presumably you know how to compute this with backprop or whatever. And here what you get the sum, and I very much encourage you to do this calculation yourself by hand, to go from here to here. It's a useful thing to do. What you get is the sum over y of the gradient of the energy with respect to W for this particular value of y, weighted by the probability our model gives to this particular value of y. Okay? So this is like an expectation of the gradient of the energy with respect to W. And the expectation is taken over the distribution that our model gives to y. Okay? The conditional distribution our model gives to over y. So you will observe that for the value of y that's equal to yi inside this sum, okay, this guy here pushes down with a force of 1 the energy of the correct answer. And this guy, because of the negative sign, pushes up the energy of the correct answer with a force equal to the probability that our model gives to this correct answer. Okay? So if our model gives probability 1 to the correct answer, then those two things will balance. Okay? And our loss function is happy. Okay? So this loss function tends to make the probability, the P of y given x for the correct answer, as large as possible. And as a consequence, because it's normalized, the other probabilities go as low as possible. So this is what happens here in this little example if you use the negative likelihood. So here I've approximated this integral here by a discrete sum over the grid. You can do this for a small dimensional problem like this. In practice, for large problems, you can't, but you have to use all kinds of tricks to approximate this. But, okay. So here, again, I push down on the blue beads because of this term, and everything else is being pushed up, including the blue beads, because of that term with this force that depends on their height. So the higher they are, the lower the force. The higher they are, which means the higher the energy, the lower the probability, and the smaller the force. Okay, so as a point is being pushed up, the force with which it's being pushed up decreases. But eventually you get a groove around the blue beads. There's kind of an interesting phenomenon here, which is that the energy of the blue beads is not all the same for all the blue beads. The only thing that matters is that the energy of the blue beads for a given value of x be the smallest for all values of y, but it doesn't matter what the absolute value is. And so they actually have different values. There's kind of a dip here, right there. And it's just because this loss function actually is invariant to an additive constant on the energy. So if I add a constant to this energy, inside of it, the loss doesn't change. I can shift the entire energy up or down, the loss doesn't make any difference. It only cares about the shape, it doesn't care about the absolute value of that energy. So let's see how that reduces, to what that reduces for binary classification. Okay, so if I binary classification, again, the energy function is minus yi gw of xi, where gw of xi is a parameterized function. For overall loss, just writing what I had before, is the average returning samples of the energy of the correct answer plus the log of the sum of the energies of the incorrect answer, where the sum is over values of y, but here we only have two values of y, y equals plus 1 and y equals minus 1, which I can express as y equals yi or y equals minus yi. Okay, so I get these two terms here. And with a little bit of manipulation, you can reduce this whole expression here to that. And that's just a logistic regression loss. Okay. If GW of x is linearly parameterized so that GW of x is W transpose phi of x, where phi is a bunch of feature functions, then you get the usual loss function for logistic regression. And somehow the Young will disappear, but you know what it is. Okay, so here is this framework, energy-based model, or energy-based learning. And then I've kind of reformulated some classical algorithms in them. I have not made the hypothesis that the energy function in most of those things, the treatment, that the energy function is a linear parameterized function of W, which allows us to use deep learning systems and stuff like that. And that's what you want to do when you do speech recognition or handwriting recognition or any kind of structure prediction with deep learning. That's what you want to do. Okay, I don't want to go into too many details about this, but so there is a paper that is going to be recommended reading, a tutorial on energy-based models. It explains, so it gives you a condition for what makes a good loss function. It's not always easy to figure out if a loss function actually does the right thing. And it's a sufficient condition. It's not, this is a condition, but basically it's the same drawing as I had before. What you want is that you want the energy is kind of somewhere to the left and above in this diagram, where this is the energy of the correct answer, this is the energy of the most fitting incorrect answer. you want the energy to be lower in this part than it is in that part. And if that's the case, then you have a good loss function. So here is a laundry list of loss functions. And whether they actually have a non-zero margin. So we already saw that the energy loss, so the thing that just pulls down on the blue beads and makes the energy of the correct answer low, does not have a margin. It can result in flat energy surfaces, so it's bad, no margin. The perceptron loss has zero margin, which is bad too. It just happens to work when the energy is linearly parameterized to W, but otherwise it probably doesn't. Hinge loss is great. It's got a fixed margin N, fine. Log loss is great too. In fact, its margin is infinite. It tries to push the energy of incorrect answers to infinity with exponentially decaying force, but it's still pushing them to infinity. LVQ2 has a zero margin, unfortunately. NCE has a margin larger than zero, but not clear what it is. Square loss has a margin. Square exponential has a margin, probably infinite. Negative log likelihood has a margin, which is infinite. So this is kind of the generalized version of that, if you want. This is another loss that people use in speech recognition, which I'm going to go into. Okay. So there are, one question you could ask yourself is why not just use this all the time? Because, it gives us probabilities, it's, it's good. The main issue with this is that this integral might be intractable. First of all, it may not converge. Second, it might be intractable, difficult to compute or approximate. So in that case, you're better off using something like that. Okay. In fact, there is a more general form for loss function. Unfortunately, I don't have a board, so I'm going to draw it here. I'm going to try to make this big so that you can see it. So the loss function would be something like sum over y of energy of yi outside W minus energy of y inside W plus d of y yi. Okay, so this is for a single sample. Okay, so let me repeat for those of you who are far away who can't read. Can you read down there? Okay, vaguely. So this is the energy of the correct answer. This is the energy of some answer. Okay, all answers, in fact, we're going to sum over all answers here. This could be an integral if y were continuous. And then we're going to have kind of a penalty function here that tells us how we think y is different from yi. Okay, this is actually kind of a more generic, a more general loss function than the hinge, because it allows us to kind of rate, how we penalize the system for confusing a particular y for the answer we want. Okay, so this D here, you could think of it as a cost matrix that tells us, if you confuse this with that, then you pay so much. And that's kind of a margin, yes.
This is the general form of any loss function, or what is it?
Say again?
What is that? That's just some loss function?
So it's kind of like the hinge loss, but a little more general, because it allows you to have these pairwise costs between pairs of categories, or pairs of answers. They don't necessarily need to be categories. So you could think of this as like a margin in a hinge loss, and the margin you're going to use depends on the two categories that you confuse. So there's no notion of most offending incorrect answer here, right? Because there is a sum of all answers. So you pay, right? So what this will try to do is that it will try to make the energy of the correct answer smaller than the energy of all answers. And for each answer, there is a different margin by which you need to make the energy of the incorrect answer larger than the energy of the correct answer. That margin depends on, how important you think to not confuse one category and another. Okay, so there's going to be a lot of versions of this, particularly for unsupervised learning, where it's very difficult to figure out how to pick say a most often incorrect answer, or how to make a sum over all y's, because y may be a very high dimensional space. And this is where unsupervised learning becomes complicated. And one of the things that we're going to talk about in future weeks is various tricks to essentially make sure the energy of incorrect answers in unsupervised learning, which means points that are outside the region of high data density, get higher energy than the data points themselves. And there's a number of different strategies for this, which I'll go to when we talk about unsupervised learning. Okay, any question? More questions? Yes?
Are there mathematical descriptions for the capacity of the network?
Well, okay, so the issues of capacities are not different from the usual ones. So it's not because we use this framework that the issues of whether you have to regularize, whether how many train samples you need, what architecture you give to the box, the GW of x you put inside of the energy function. All those problems still exist, and they don't exist any less or any more. It's the same. Okay. So if your energy function has infinite VC dimension and is not regularized, then it's not going to work, right? Or probably not. So either you need to regularize or limit the capacity of the box that you put inside. Yes?
If y is continuous, do you just define some sort of continuous margin? Or?
Well, this could be a continuous function.
Sure.
Right? So that defines...
So you choose some Gaussian?
Well, yeah, it could be a quadratic function, that is just a function of the square distance between those two things.
Okay.
That's the simplest case, but you can imagine other things.
So are performances of any of these loss functions sensitive to how one defines the least offensive?
Least offending answer? Well, least offending answer is well defined.
But right? For example, for continuous cases,
oh, for continuous case, yeah. Right.
And even for classification cases, one could, for example, say the least offending answer is the energy of the second lowest, right? But couldn't you also say energy of the average, or average of all the other wrong answers? So
the problem with the energy of the average of all the other answers is that it does not guarantee that in the end, when you minimize the loss, the inference algorithm will give you the correct answer, right? You could very well have a high average for the incorrect answers, but one of those could be very low and lower than the correct answer, and then it will give you the wrong answer. So at least if the minimum, if the smallest of all is above the correct answer, then you guarantee the system will give the right answer. Okay, so there's an important question for things like ranking. So in ranking, you don't care, there's no correct answer, essentially. It's just a complete or partial ranking of the answers. And you just want them to be in an order that's compatible with the constraints that you put on the rank. Okay, so for example, ad placement or newsfeed ranking is one of those problems where you want the most important things to come at the top, but you don't know the complete order. So there's a lot of things you could display, say in the newsfeed for Facebook, for example, and you don't have a complete ranking for all of the things that the person might be interested in. In the end, you show a certain number of things to people, and they click on the ones that they're interested in. They actually look at them or they respond to them. That's an indication that they were interesting to them. But you don't have any information on the ones that they didn't click on, well, you have information on the ones they didn't click on. You don't have information on the ones you didn't show them. There is other kind of issues of feedback and stuff like that. But so there you get a partial ranking. You know that the ones that have been clicked on are better than the ones that have not been clicked on. For the ones you didn't show, you have no information. So you have a partial order. And your loss function could be, do I respect this partial order or not in the training set. Those are kind of ranking criteria. And the ranking criteria are very much like this. So they have things that say, okay, I know the person clicked on this one and didn't click on that one, so I want the energy for that guy to be lower than that guy because then you're going to show it more often. Right. So there's going to be a guest lecture by Jason Weston in a few weeks. That I think it's the week after spring break, 24th. It's going to talk about those ranking criteria and how you can use this for search. Jason is was a research scientist at Google and just joined Facebook, and he's basically in my group at Facebook, and has worked on ranking and various other applications. Interesting lecture. Other questions?
Sorry, I don't quite understand the D there. EYYR doesn't describe the variance of Y.
It's not a variance. It's a substitution cost. Okay, so it's how much do you pay for making those two energies the same, right? So if the correct answer is yi, and here y is a particular incorrect answer, if those two energies are the same, you pay this cost. Okay, that's what it means. And so what it says is that you're going to push this down, so that this value is lower than that one by at least that much.
Does it include a W in it?
Yeah, okay, I forgot a term here. It's a positive part of that. I'm sorry, it's a hinge, right? So basically, this is like a loss function that says, as a function of the difference between the correct energy and the incorrect energy, it's like this. This is minus d. Okay, so it wants to make the energy of that lower than the energy of that, by at least this d. And this d would be different for different pairs of y and yi. Okay. Sorry about the plus. Any other question? Yes.
So we're going to start having assignments.
Yeah, Chang here is laughing because he's the one writing the code for the assignment. Yeah, it's coming really soon.
Is it slides on the website?
Sorry, on the website also, yes. That's another issue. I'm sure we'll fix soon. Most of them, so the videos, some of them are on the TechTalks.tv, but some of them were botched for some reason. So there's no audio on the tutorial for Torch, which is kind of painful. And not all of them have been posted. So, I mean, I looked at some of them, and not all of them are there. Some of them are there twice, so my guess is that there was also a substitution between the files.
So we have a project as final and assignment.
Yeah.
That's it.
Yeah. Any other questions? More questions?
Yeah.
Yes.
Will there be midterm?
No midterm. No, it's just the assignments. Assignments and midterms. Okay, first assignment is going to be implementing some funny modules, training neural nets of various kinds, and see if it works. Sometimes it won't.
Can we do after spring break?
It will be after spring break, yes. Because, well, really? Actually, that's a good question. Yeah, we can probably do that into spring break. I mean, the first one is not going to be that hard. We'll give a couple of weeks for the homework, but the next homework is probably going to come before the first one is due, so you get an idea of what to expect.
What's the project timeline?
Project, it's probably about 5 weeks before the end of the semester. If you have an idea for a project that you really want to do, just come to me. Just write a paragraph or two, send it to me by email, and I'll say yes or no. And if you have a good idea, you can start working on it pretty quickly.
What are the team sizes?
So team sizes, the recommended team sizes is 1 or 2. 2 is fine. 3, you really have to justify yourself. So if it's like an ambitious project and you really think you need 3 people, I might make some exceptions, but there'll be exceptions.
And we could start working on the project right now.
If you had a good idea for a project, yes.
Do you have final?
Most likely, yes.
Will we work a lot?
It's probably going to be, what was the weighting between the different things? The project would count for quite a bit, probably like 40%, and then the 30 for assignment and final.
Which convince you not to have
Well, actually, it's easier for me because I don't have to write it.
Yeah.
But I think it's not going to be a complicated. But I think it's useful because it allows you to kind of see what's important and you to kind of. It's not going to be the end. And if you if you understood most of the material, you read the slides, you read the recommended reading, you've done the homework and you've understood the homework. If you let someone else do the homework, it's not going to work. Okay, so I mean the homework are there for you to learn. The assignments are there for you to learn the material, and so do the assignment. That's the main thing. Even if it counts for like a third, it's important because that's how you learn things. If you don't do the assignment, you're in trouble.
Just one thing, you upload the slides that you actually use then in the lectures to the wiki page? Because now there are slides which are like other.
They are. No, I think the ones I've uploaded is the one that I used, but they are in one file instead of multiple ones.
Not always.
Not all of them is. No. It's just the only one. So.
But you must have the slides on your computer.
I do.
Right? So.
Yes. Okay. No more questions?